Okay, welcome back to part 2 of our lecture on production of power from heat. And we will continue with the given problem. First, let's review the problem. Alright, so we're given a Rankine cycle or Rankine cycle, depending on whether you're British or American. Uh, wherein steam is superheated to 1000 degrees Fahrenheit. We're given the efficiency of the turbine and also the after expansion pressure, the inlet and outlet pressure of the turbine. So P2 and P3 work work required by the pump is negligible. We're also given the work generated by the turbine. What is required from us is the mass of flowing stream and the heat absorbed in the boiler. So to calculate these values, remember we can calculate the mass of flowing stream using uh, using the equation. Okay, so I think this is wrong. We should base it on the actual. So let me correct this. We should base it on the actual work and the how to erase this. Okay, eraser is this. Let me try this one. Okay. Let's base it on the actual work. Work shaft equal to delta HS times mass of flowing stream. Okay, so this one is not. Let's disconnect it from this one. Okay. And then so far what we did was to for each point we calculated some values that we um can calculate or read from the steam table. For example, at point 2 it's superheated steam. So we know the conditions at point 2, the P2 and T2. So from the steam table we read the enthalpy and entropy. And we use this entropy S2 to find the isentropic um, value of at point 3, isentropic expansion entropy at point 3. They should be equal because this is a vertical line. And then from there, we calculated the quality at at point 3 prime. Okay, the quality here, which is x prime, and we use that to calculate for H3 prime. Okay, using the saturated properties of the enthalpy at point 3. Okay, and then next, from there, so we have the value of H3 prime, and now we know the value of delta H ideal because it's simply H3 prime minus H2. So what do we do with this value? How can we use it? Remember that we are given um, the efficiency of the turbine. And what we want to know is mass of flowing stream. We are given already, uh, this is given. This is something that we can calculate and this is required. Okay. So what we can do is to use the efficiency of the turbine the turbine efficiency, remember it's the delta H ideal over the delta H act oops. Yeah, actual. Something is wrong. No, baliktad. Sa pump yung delta HS sa taas. So, delta H actual because it's smaller over delta H ideal. Okay? Delta H and ideal. And we know given this turbine efficiency is given, it's 0.75%. So we put here 0.75. Okay, 0.75. And we know, we know delta H ideal. So we can calculate for delta H actual, which is just 0.75 times delta H ideal na nakuha natin earlier, negative 455. So negative 455.8599. Delta H actual is negative 341.845 BTU per pound mass. So now we can use this equation. There's no S here. Correction again. There should not be an S here. Okay. How do we erase that? Sige. This is delta H lang actual. Delta H. Okay? We use that equation to calculate for the mass of flowing stream. So the mass of flowing stream is sige. So the mass of flowing stream is equal to WS or work shaft divided by delta H. And this is 200,000 kilowatts. Okay. Given yan. Divided by negative 341. Yun lang. BTU per pound mass. So we need to convert the values. So by the way, this one should be negative because it's the it's a work done by the system. So oops. This one should be negative, work done by the system. Okay? So how do we convert it? We convert it to so let's just use some conversion factors like BTU to kilojoules because this one right here is so we multiply the numerator with conversion factor of 0. So any conversion factor that would help you convert to BTU. So it depends on you what you will use. But anyway, this is what I use. So this is 189,563, 563, 189,563.4 BTU per second divided by 341, negative 341.845 BTU per pound mass. So what will be left is pound mass per second, which is the unit of the mass flow rate. And the mass flow rate is 554.53 pound mass per second. So that's MFS. That's the answer. Okay, we're halfway done with the required. So now let's try to solve for QH. QH. So this QH is the heat absorbed in the boiler. Okay. And that would be H2 minus H. Heat absorbed. Ano ba? QH. Parang may mali. Oh no. The heat rejected in the condenser, not QH, but rather QC. It's QC, not QH. So let's delete na lang to and put here QC. Okay? Heat released in the condenser, and the equation for that is, diba, it's QC is, or is delta H, okay, times the mass of the flowing stream. And this is H4 minus H3. Since we already calculated H3, our goal now is to look for H4. Diba? We have a value for H3. Nasaan yun? We don't have it yet, but we have the delta H actual. So simply, we can calculate for H3 from delta H actual. So in the turbine, diba, if you remember, this is the equation of um for the turbine, delta H is H3 minus H2. But we know delta H, we have a value negative 341, and we know H2. So H3 is delta H plus H2, which is equal to negative 341.845, okay, plus H2, which is, what's our H2? 1.5. Sa steam table sa taas, sa pinakauna. Diba? Balikan natin. H2. Here. by H2. H2 is 1520.3. So H3 is 1178.455. Okay? So QC, or heat rejected from the condenser, is H4 minus H3. Okay, why? Why again? Balikan natin si TS diagram. Diba? This is the condenser right here. So, delta H of the condenser is equal to QC, and that's H4 minus H3. Alright, so do we know H4? Not yet. We don't know H4, but we know that 0.4 is a saturated liquid. Okay, so we're already at 0.4. It's a saturated liquid. From the steam table, H4, from the steam table, H4 is, kung saturated liquid yan, okay, and we know, sabi sa problem, we know that P4 equal to P3 equal to 5 PSIA. From the steam table, we can immediately read H4. Okay. Why? Hindi na kailangan ng quality kasi nandun na siya sa saturated liquid line. Okay, so it's purely saturated liquid. We know the H4, so it's the H4L. Then from the steam table, it's 130.2 BTU per pound mass. Okay. So now that we have both H4 and H3, QC is now 130.2. 130.2 minus H3, 1178.455, and this is negative 1048.255 BTU per pound mass. QC. Okay. So, if we want to express this in terms of uh rate, so this actually should be multiplied by the mass of flowing stream. So we just multiply everything by the mass of flowing stream to express this value as a rate. Okay, so we multiply it with what's the mass of flowing stream? 554. Ay, na-solve natin kanina. So, times 554.53. Our QC is actually 581,288.84. This point, and this is BTU per second. Okay, so that's our answer. Do you have, I can't ask if you have questions, just post them, your questions, on our Google Classroom. Okay, so to recap our problem, Ayan, so this is, we began by drawing the TS diagram, and at each point, we try to identify what's given in the problem. Okay. And then, based on what is required, we flesh out the equations that will give us the required values. Like for mass of flowing stream, diba, we calculated it from the equation of the turbine right here, equation of the turbine. So again, we can use the isentropic expansion properties to calculate the quality of the steam, and therefore H3 prime, and then we use the efficiency of the turbine to calculate the actual delta H. Diba? This is the actual delta H, and we use that to calculate the mass of the flowing stream. And then for the last part, for QC, we calculated it using the properties of the condenser, inlet and outlet properties of the condenser. All right, so we'll move on to the next sample problem. Consider a steam power plant operating on a Rankine cycle. Steam is superheated to 450 degrees Celsius at 5,000 kilopascals and exhausts at 20 kilopascals. If the efficiency of the turbine is 80% and the efficiency of the pump is 75%, determine the thermal efficiency of the cycle. Okay. Um, let's solve it right here beside our first problem. So given, uh, let's draw the TS diagram first. TS diagram, so given a Rankine cycle, it was not mentioned whether there's subcooling, so there's no subcooling, so let's assume that there is subcooling, otherwise it will be mentioned in the problem. Okay, so if there's subcooling, then the cycle begins at the entry of the boiler. Okay, so boiler is superheated to um and then there's turbine expansion, and then all right, let's do that again. Point 4. So by the way, the pump here is exaggerated, the lines for the pump. Usually it's just very small. So this is point 1. Entry, by convention, entry to the boiler is point 1. And then this is point 2, uh, expansion. I mean, entry to the turbine. Entry to the boiler, point 1. Entry to the turbine, point 2. Entry to the condenser, point 3. And then we have 3 prime here. Then entry to the pump, 4. Okay. So this is a Rankine cycle. So what's given to us is T2. T2 equal to 450 degrees Celsius, and P2 is 5,000 kilopascals. and exhaust at P3 20 kilopascals. Efficiency of the turbine is 80%. Efficiency of the pump is 75%. 75%. Okay. Next is what is required. The end of the entire cycle. Okay. So since the pump, the efficiency of the pump is given, we cannot neglect the work required of the pump, and therefore the efficiency of the entire cycle would consider the um, work of the pump. So it's the work of the produced by a turbine plus the work required by the pump over QH. So by convention, this would have a negative value and this would be a positive value. And we're going to take the absolute value of that. Okay. So we begin at the analysis at point 2, which is the superheated vapor at the entry of the turbine. Point 2, superheated vapor or steam. So at this point, it's P2 5,000, T2 450 degrees Celsius. We can easily read the properties from the steam table, which are from the steam table from ST, SH2 is 3317.5 kilojoules per kilogram. And then S2 is 6.8217 kilojoules per kilogram Kelvin. Okay. So that's at point 2. For point 3, we have what is point 3? Wet steam, diba? Wet steam, wet steam. So we know that P3 is 20 kilopascal. Automatically, since it's saturated, then we would know from the saturated properties that T3 is 60.09 degrees Celsius. Okay, from the steam table. So if we consider the isentropic expansion of the turbine at point 2 to point 3 prime, we can read therefore yung S3 prime, okay, from uh, the steam table kasi it's just simply the saturated, the entropy at P3 and T3. No, no, no. I'm sorry, that's wrong. So, um, we don't read it from the steam table. Okay? So how do we know it? We equate it to S3 prime. Kanina siya equate? S2. Kasi it's vertical line. It's a vertical line. Therefore, As you can see, vertical S2 equal to S3 prime. Correct? Okay, so it's just equal to 6.8217. Right? Yan. Diba? Next is from the steam table. Ito we can read it. From steam table, okay, we know S3L is 0.8321. Oops. And then S3V 7.9094. Diba? So S3 prime, so therefore, using this values S3 prime and uh, the liquid and vapor entropies, we can calculate for X prime, the quality of steam at the at 3 prime. Okay, so X prime yun. Quality of the steam at X prime. Diba? So just make an equation. S3L times 1 minus X prime plus S3V times X prime. Okay. Plug in everything. Meron ka na nito, ito. X prime is 0.8463. Okay. So what are we looking for again? And uh, so the end of the cycle. So let's go back to this equation. Diba? If you remember from the lecture, how do we solve this? It's just so it's just H3 minus H2 plus H1 minus H4, diba? So this is for the turbine. This is the work of the turbine. This is for the work required by the pump. And then QH is simply H2 minus H1. The mass of flowing stream got cancelled. Okay. So that's why we're looking for H1, H2, all the H's for all of the steps. Okay? That's why, yan, may H2 na tayo, yeah, we can calculate for H3 next. So, we now calculate H3 prime. And based on the value, so from the steam table, H3L is 2609.9. H3V is yan, 251.453. So plugging all of that, X prime and all of these, this one, we calculate for X prime. I'm sorry, H3 prime. And it's 2247.43. Okay. And then we use the efficiency of the turbine to calculate for the actual. Kasi the efficiency of the turbine, and minus taas the lower value, which is the delta H actual over delta HS. So this is H3 minus H2, H3 prime minus H2. So, plugging in all of the values, diba, we have H2 na from step 2 sa taas. Then, we have H3 prime. Plugging in all the values. Uh, and this is equal to the efficiency of the turbine, which is given 80%. So, 0.8. Okay, so everything is known here except for H3. And solving for H3, it's negative 856.056. Okay. So, let's move to point 4 na. Point 4, it's saturated liquid. Saturated liquid. Saturated liquid. And given is point four, P4, P3. You know P3, and then it's just a straight horizontal line. So, it's an isobar. So, 20 kilopascals. We know the entry point to the pump inlet is at 20 kilopascals. Since it's saturated liquid, automatically from the steam table, we would know that it's 60, T4 is 60.09 degrees Celsius. And we can read the properties of saturated liquid at this point, each for 251.453 kilojoules per kilogram. And we need also yung V4. Okay. So, it's 1.017 cm cube per gram. So, if you will remember that for uh, for the pump, the equation is delta H equal to V delta P. Okay. Uh, so we know the uh, okay, so this is specially derived, if you will remember, it was derived by assuming isentropic uh, compression, isentropic conditions for the pump. So this is delta HS. So that is V4 times P1 minus P4. Pabalikan natin yung pump. Diba, ito yun. V4 V1 minus P1 minus P4. P1 minus P4. So delta HS is so convert this value to meter cube per kilogram. Diretso ko na, and that's 0.001017 meter cube per kilogram. So this is just this value times 5,000 uh, minus 20, and that is kilonewtons. The kilopascal is kilonewtons per meter squared. And ang mangyayari dyan ay maging kilonewton meter per kilogram, which is just kilojoules. Okay, so 5.0647 kilojoules per kilogram. Next, so we have the delta HS of the pump. We calculate for the actual. So remember, the efficiency of the pump, ano yung nasa taas? yung isentropic. Okay, kasi it's smaller, has a smaller value. So, what we want is this. The delta H is delta H isentropic times the efficiency of the pump. And just plug in everything. Delta H is... I did not calculate it. Hindi, ito, I calculated it. 5, wait, just a minute. Ayan, the value is 6.752. Oops. Okay. Kasi efficiency of the pump is 0.8. So that's a given. So plug in all the values. We know this, we know that. Tama ba? Work required of the pump is smaller. Okay, so uh tama. The isentropic work is in the numerator. So the delta H is... So delta H, mali yung ano ko. Ito yung mali. Sorry about that, guys. Mali yung transformation ko ng equation. Delta H is delta H S over efficiency of the pump. Okay, so we know this, diba? It's 5.0647 and the efficiency is 0.8. So just plug in the values and we will get 6.75288. Okay, kilojoules per kilogram. So now that we know delta H, we can use it to calculate H sub 1. Kasi we have H sub 4. And delta H at this point is, diba, this is the pump. So we're talking about the pump. The pump, so H1 minus H4. H1 minus H4. Therefore, H1 is delta H plus H4, which is delta H is 6 point um mm, 251 and then 6 point delta H is 6.75288 plus 251. 251.453. So that is H4. Diba? Yung pinaka, nasaan yung H4? 251.453 here. Therefore, H1 is 258. 258.20558. 20588 pala. 20588. Okay. Uh, so do we have all the values? H1, H4, H3, and H2. Okay, so we now have all the HS. We go back to the equation. We go back to this equation and plug in the values. Diba? Plug in the values. So the efficiency of the entire cycle. Remember, it's the pump. I mean the turbine first, H3 minus H2 plus for the pump H1 minus H4 divided by QH, which is H2 minus H1. Balikan natin kung tama. H minus H2, yan, tama. So, plug in everything. What you will get there is 27.76%. So, it means that out of the heat absorbed, in the boiler, which is this value, and that value is, lagay ko dito, yung heat absorbed sa boiler, QH yan, 3,059.2941 kilojoules per kilogram. Out of that value, only 27.76% is converted to work. Kasi, so may work generated by the turbine, but we have to subtract yung work required by the pump. Okay, so here the work net. Okay, so this is work net. That value is 849.30312.